Higher dimensional supergravity. Higher dimensional supergravity is the supersymmetric generalization of general relativity in higher dimensions. Supergravity can be formulated in any number of dimensions up to 11. This article focuses upon supergravity SUGRA in greater than 4 dimensions. Supermultiplets, fields related by supersymmetry transformations form a supermultiplet. The one that contains a graviton is called the supergravity multiplet. The name of a supergravity theory generally includes the number of dimensions of spacetime that it inhabits, and also the number n \displaystyle \mathcal n of gravitinos that it has. Sometimes one also includes the choices of supermultiplets in the name of theory. For example, and n equals 2 \mathcal n equals 2. 9 plus one-dimensional supergravity enjoys 9 spatial dimensions, 1 time, and 2 gravitinos. While the field content of different supergravity theories varies considerably, all supergravity theories contain at least one gravitino, and they all contain a single graviton. Thus, every supergravity theory contains a single supergravity supermultiplet. It is still not known whether one can construct theories with multiple gravitons that are not equivalent to multiple decoupled theories with a single graviton in each. In maximal supergravity theories, see below, all fields are related by supersymmetry transformations so that there is only one supermultiplet, the supergravity multiplet. Gauged supergravity versus Yang-Mills supergravity. Often an abusive nomenclature is used when gauged supergravity refers to a supergravity theory in which fields in the theory are charged with respect to vector fields in the theory. However, when the distinction is important, the following is the correct nomenclature. If a global, i.e. rigid R-symmetry is gauged, the gravitino is charged with respect to some vector fields, and the theory is called gauged supergravity. When other global rigid symmetries, e.g., if the theory is a nonlinear sigma model of the theory, are gauged such that some non-gravitino fields are charged with respect to vectors, it is known as a Yang-Mills-Einstein supergravity theory. Of course, one can imagine having a gauged Yang-Mills-Einstein theory using a combination of the above gaugings. Counting gravitinos. Gravitinos are fermions, which means that according to the spin statistics theorem they must have an odd number of spinorial indices. In fact, the gravitino field has one spinor and one vector index, which means that gravitinos transform as a tensor product of a spinorial representation and the vector representation of the Lorentz group. This is a Rarita-Schwinger spinor. While there is only one vector representation for each Lorentz group, in general there are several different spinorial representations. Technically, these are really representations of the double cover of the Lorentz group called a spin group. The canonical example of a spinorial representation is the Dirac spinor, which exists in every number of space-time dimensions. However, the Dirac spinor representation is not always irreducible. When calculating the number n \mathcal n, one always counts the number of real irreducible representations. The spinors with spins less than 3/2 that exist in each number of dimensions will be classified in the following subsection. A classification of spinors, choosing chiralities, counting supersymmetries. All supergravity theories are invariant under transformations in the Superpoincare algebra, although individual configurations are not in general invariant under every transformation in this group. The Superpoincare group is generated by the Superpoincare algebra, which is a Lie superalgebra. A Lie superalgebra is A, Z, E, 2, \math Z2. Graded algebra, in which the elements of degree 0 are called bosonic and those of degree 1 are called fermionic. A commutator that is an antisymmetric bracket satisfying the Jacobi identity is defined between each pair of generators of fixed degree except for pairs of fermionic generators. for which instead one defines a symmetric bracket called an anticommutator. The fermionic generators are also called supercharges. Any configuration which is invariant under any of the supercharges is said to be BPS, and often non-renormalization theorems demonstrate that such states are particularly easily treated because they are unaffected by many quantum corrections. The supercharges transform as spinors, and the number of irreducible spinors of these fermionic generators is equal to the number of gravitinos, n \display style \mathcal n, defined above. Often, n \display style \mathcal n is defined to be the number of fermionic generators instead of the number of gravitinos, because this definition extends to supersymmetric theories without gravity. Sometimes it is convenient to characterize theories not by the number n \display style \mathcal n of irreducible representations of gravitinos or supercharges, but instead by the total Q of their dimensions. This is because some features of the theory have the same Q dependence in any number of dimensions. For example, one is often only interested in theories in which all particles have spin less than or equal to 2. This requires that Q not exceed 32, except possibly in special cases in which the supersymmetry is realized in an unconventional, nonlinear fashion with products of bosonic generators in the anticommutators of the fermionic generators. Examples: maximal supergravity. The supergravity theories that have attracted the most interest contain no spins higher than 2. This means, in particular, that they do not contain any fields that transform as symmetric tensors of rank higher than 2 under Lorentz transformations. The consistency of interacting higher spin field theories is, however, presently a field of very active interest. The supercharges in every super-Poincare algebra are generated by a multiplicative basis of m fundamental supercharges, and an additive basis of the supercharges. This definition of supercharges is a bit more broad than that given above is given by a product of any subset of these m fundamental supercharges. The number of subsets of m elements is 2, thus the space of supercharges is 2-dimensional. The fields in a supersymmetric theory form representations of the super-Poincare algebra. It can be shown that when m is greater than 5 there are no representations that contain only fields of spin less than or equal to 2. Thus we are interested in the case in which m is less than or equal to 5, which means that the maximal number of supercharges is 32. A supergravity theory with precisely 32 supersymmetries is known as a maximal supergravity. Above we saw that the number of supercharges in a spinor depends on the dimension and the signature of spacetime. The supercharges occur in spinors. Thus the above limit on the number of supercharges cannot be satisfied in a spacetime of arbitrary dimension. Below we will describe some of the cases in which it is satisfied. A 12-dimensional two-time theory. The highest dimension in which spinors exist with only 32 supercharges is 12. If there are 11 spatial directions and one time direction, then there will be Weyl and Majorana spinors, which both are of dimension 64, and so are too large. However, some authors have considered nonlinear actions of the supersymmetry in which higher spin fields may not appear. If instead one considers 10 spatial direction and a second temporal dimension, then there is a Majorana-Weyl spinor, which as desired has only 32 components. For an overview of two-time theories by one of their main proponents, Itzhak Bars, see his paper Two-Time Physics and Two-Time Physics on arXiv.org. He considered 12-dimensional supergravity and supergravity, p-brane duality, and hidden space and time dimensions. It was widely, but not universally, thought that two-time theories may have problems. For example, there could be causality problems, disconnect between cause and effect, and unitarity problems, negative probability, ghosts. Also, the Hamiltonian-based approach to quantum mechanics may have to be modified in the presence of a second Hamiltonian for the other time. However, in two-time physics it was demonstrated that such potential problems are solved with an appropriate gauge symmetry. Some other two-time theories describe low-energy behavior, such as Kamran-Boffa's F-theory, that is also formulated with the help of 12 dimensions. F-theory itself, however, is not a two-time theory. One can understand 2 of the 12 dimensions of F-theory as a bookkeeping device. They should not be confused with the other 10 spacetime coordinates. These 2 dimensions are somehow dual to each other and should not be treated independently. 11-dimensional maximal SUGRA. This maximal supergravity is the classical limit of M-theory. Classically, we have only one 11-dimensional supergravity theory, 7D hyperspace plus 4 common dimensions. Like all maximal supergravities, it contains a single supermultiplet, the supergravity supermultiplet containing the graviton, a Majorana gravitino, and a 3-form gauge field often called the C field. It contains 2 p-brane solutions, a 2-brane and a 5-brane, which are electrically and magnetically charged, respectively, with respect to the C field. This means that 2-brane and 5-brane charge are the violations of the Bianchi identities. The supergravity 2-brane and 5-brane are the long wavelength limits. See also the historical survey above of the M2-brane and M5-brane in M-theory. 10 SUGRA theories. Type IIA SUGRA N equals 1, 1. IIA SUGRA from 11 SUGRA. IIA SUGRA is the dimensional reduction of 11-dimensional supergravity on a circle. This means that 11 supergravity on the spacetime M 10 x s 1 backslash display style M10 backslash times S1 backslash is equivalent to IIA supergravity on the 10 manifold M 10 backslash display style M10 backslash slash, where one eliminates modes with masses proportional to the inverse radius of the circle shown. In particular, the field and brane content of IIA supergravity can be derived via this dimensional reduction procedure. The field G E 0 backslash display style G0, however, does not arise from the dimensional reduction. Massive IIA is not known to be the dimensional reduction of any higher dimensional theory. The one-form Raymond potential C E 1 backslash display style C1 backslash is the usual one-form connection that arises from the Kaluza-Klein procedure. It arises from the components of the 11D metric that contain one index along the compactified circle. The IIA 3-form gauge potential C E 3 backslash display style C3 backslash is the reduction of the 11 3-form gauge potential components with indices that do not lie along the circle, while the IIA Kalb-Raymond 2-form B field consists of those components of the 11-dimensional 3-form with one index along the circle. The higher forms in IIA are not independent degrees of freedom, but are obtained from the lower forms using Hodge duality. Similarly, the IIA branes descend from the 11-dimension branes and geometry. The IIA D0 brane is a Kaluza-Klein momentum mode along the compactified circle. The IIA fundamental string is an 11-dimensional membrane which wraps the compactified circle. The IIA D2 brane is an 11-dimensional membrane that does not wrap the compactified circle. The IIA D4 brane is an 11-dimensional 5 brane. The IIA S5 brane is an 11-dimensional 5 brane that does not wrap the compactified circle. The IIA D6 brane is a Kaluza-Klein monopole. That is a topological defect in the compact circle fibration. The lift of the IIA date brane to 11 dimensions is not known, as one side of the IIA geometry, as a non-trivial Romans mass, and an 11-dimensional original of the Romans mass is unknown. Type IIB SUGRA N equals 2, 0, 0, 0. Type I gauged SUGRA N equals 1, 0. 9 SUGRA theories. In nine-dimensional Minkowski space, the only irreducible spinor representation is the Majorana spinor, which has 16 components. Thus, supercharges inhabit Majorana spinors, of which there are at most 2. Maximal 9 SUGRA from 10. In particular, if there are 2 Majorana spinors, then one obtains the 9-dimensional maximal supergravity theory. Recall that in 10 dimensions, there were 2 inequivalent maximal supergravity theories, IIA and IIB. The dimensional reduction of either IIA or IIB on a circle is the unique 9-dimensional supergravity. In other words, IIA or IIB on the product of a 9-dimensional space M9 and a circle is equivalent to the 9-dimension theory on M9, with Kaluza-Klein modes, if one does not take the limit in which the circle shrinks to 0. T-duality. More generally, one could consider the 10-dimensional theory on a non-trivial circle bundle over M9. Dimensional reduction still leads to a 9-dimensional theory on M9, but with a 1-form gauge potential equal to the connection of the circle bundle and a 2-form field strength which is equal to the Chern class of the old circle bundle. One may then lift this theory to the other 10-dimensional theory, in which case one finds that the 1-form gauge potential lifts to the Kalb-Raymond field. Similarly, the connection of the fibration of the circle in the second 10-dimensional theory is the integral of the Kalb-Raymond field of the original theory over the compactified circle. This transformation between the two 10-dimensional theories is known as T-duality. While T-duality in supergravity involves dimensional reduction and so loses information, in the full quantum string theory the extra information is stored in string winding modes, and so T-duality is a duality between the two 10-dimensional theories. The above construction can be used to obtain the relation between the circle bundle's connection and dual Kalb-Raymond field even in the full quantum theory. N equals 1 gauged SUGRA. As was the case in the parent 10-dimensional theory, 9-dimensional N equals 1 supergravity contains a single supergravity multiplet and an arbitrary number of vector multiplets. These vector multiplets may be coupled so as to admit arbitrary gauge theories, although not all possibilities have quantum completions. Unlike the 10-dimensional theory, as was described in the previous subsection, the supergravity multiplet itself contains a vector, and so there will always be at least a Yuon gauge symmetry, even in the N equals 2 case. The mathematics.